Okay, in this video we'll look at a couple of examples that show how we can use the basic rules of differentiation that we explored in the previous video to allow us to use the power rule in situations where, I guess at first glance, using the power rule doesn't seem like an option. And this function is a good example because it's the product of two functions. We have a linear 2x minus 3 multiplied by a quadratic x squared minus 4. And we're unable to differentiate this using the power rule until we expand the function. So if I expand this function, multiply it all out, then we'll have it written as a sum or difference of functions. It'll be four terms, what we would commonly call terms, but now when we're differentiating, we can see that as four different functions added and subtracted, and that's going to allow us to go through and differentiate each individual term, and like I said, utilize those basic properties. So let's expand out this function. This will be f of x equals 2x times x squared, which will be 2x cubed. And then we'll have 2x times minus 4. And then now to the negative 3 times x squared, which is negative 3x squared. And finally, negative 3 times negative 4, which is plus 12. So now hopefully we can look at this and see it really for what it is. It's a cubic polynomial function. It's a polynomial with a degree 3. The highest x power is 3. So I'm going to sort this. I don't really have to do this, but usually with polynomials I like to sort it so then I can see that I have everything in its proper place, I guess. So then we can see the powers of x descend from 3 all the way down to nothing there with the constant 12. And then we can hopefully make the connection that now, yes, we can differentiate this function by differentiating each individual piece of this function, because this function is four functions added and subtracted together. So I'm going to use the differential operator here in this, I guess, first example, which might be a little bit much, but at least it should be something that's, I guess, you're thinking, if not writing down. So I'm going to differentiate each individual piece in this function. So of course I have to differentiate 2x cubed, and then I'm going to differentiate after the subtraction 3x squared, and yes, after another subtraction we'll have to differentiate 8x, and finally after one more sum here or addition we'll differentiate the constant 12. So I'll put all those pieces in. So 2x cubed, and then we'll have 3x squared, and then we'll have 8x, and then we'll have 12. So whether you choose to write that down or not, honestly, that's your choice. But at least if you're thinking that way, that should suffice. And then you can exploit those basic properties to differentiate this function. And I'm going to go one more. Again, I'm going to write it out. If you want to just think this instead of writing it, that's fine. But remember, we can bypass coefficients, a so-called constant multiple of functions. So we can see this as the multiple of 2 multiplied by the derivative with respect to x of now just x cubed. And then we can move on to the next term. So basically we're making this just a series of very easy derivatives involving very plain power functions. So first one of degree 3, and then if we bypass this constant of 3 after this subtraction, we just get to differentiate a basic quadratic of x squared. And I guess I'll keep my color change in here. That might help you see what's happening. And like I've acknowledged a few times, this is pretty inefficient if you're taking the time to write this all out. But of course, in this first example, I want to be super clear how you can use those basic properties to differentiate a polynomial such as this. And we're almost there. The final one, I guess we just need to do a rewrite, because this is the derivative of a constant 12. So in that step, I bypassed all those coefficients, treating them like constant multiples, and now we just can go ahead and use our power rule 3 times and then deal with the derivative of the constant towards the end there as well. So this is going to be 2 multiplied by the derivative of x cubed, which of course is going to be 3x squared, and then the final step we'll just multiply those two numbers together, of course. And then after the 3, we'll have the derivative of x squared, which is going to be 2x. And off to the next one. Now you can just recognize the slope on that linear term x as 1 and write 1. And I guess the yellow brackets here, if you want to use the power rule, I guess that works as well. Although that's a little more maybe complicated. So the coefficient, the exponent on that x is 1, so that comes down in front, and then you multiply that by x to the power of 0. And then you realize, hey, x to the power of 0 is 1. And I think a far easier way of dealing with that is treat it like a linear function, that it is obviously that function of x, y equals x, and the slope of that linear function is of course the coefficient on x, which is 1. And we've explored that again in the previous video as well. So now we get to add on the derivative of the constant 12. And similarly, that's a constant function, y equals 12. That's a horizontal line. So remember, its slope of a constant horizontal line is always 0. So there it is, and I guess down to the atomic level of utilizing all those basic properties of differentiation that we explored in the previous video. And now we can put this thing together and multiply those constants we sidestep by those very simple power derivatives of power functions that we just completed there. So now we'll have 6x squared, we'll have minus 6x, and then we'll have a minus 8. And of course, there's no point in writing a plus 0. And here's our derivative. And we were supposed to find the slope of this curve somewhere, I believe. Yeah, and find the slope of the curve at x equals 2. So now that we got our derivative, the easy part is actually using it. And note, our derivative is a quadratic function in itself, our tangent slope finder. So let's put our tangent slope finder to work. What is the tangent slope at x equals 2? It'll be 6 times 2 squared minus 6 times 2. Subtract 8. So what do we got? 6 times 4, which is 24, minus 12, minus 8. So the slope of our curve is 24 minus 20, or 4. So there is our punchline. We've actually just used our derivative. Of course, finding it is all the work, but it's nice to actually use it to remind yourself what it does. And of course, it's finding the slope of our curve. Slope of the curve at a specific x value. In this case, it was x equals 2. Okay, in our next example, in our last example, we're going to differentiate this function in f of x, which is a quadratic divided by another quadratic, and find the slope of the curve at x equals 3, as after we get our derivative, of course. So again, power rule doesn't really look like an option here because this is a quotient of two functions, and we haven't dealt with quotient rules yet. And in the previous example, since it was a product, there is a product rule that we haven't dealt with yet. And honestly, even when we do deal with the quotient and product rules of differentiation, it's far easier to do what we're going to do in this video, which is just, in this case, not expand anything out, but write this as three separate quotients. Or basically realize that that x squared in the denominator can be divided into all three terms on the top. So again, we'll write this out in painstaking detail here. So that first term on the top, x squared, is all over x squared. And then that second term, after the subtraction, 6x is also over x squared. And then finally, we'll have 8 divided by that x squared as well. And then we can simplify these things and get ready, of course, for our power rule. So x squared over x squared is 1. And then I have, I guess this is 6 over x. Maybe we'll do this in 2 more steps. And this is 8 over x squared. And again, the power rule is not an option until we rewrite those x variables in the denominator, write them using negative exponents. Of course, those are powers. So here's our preliminary work. This is going to be 6 multiplied by x to the minus 1, which remember is a reciprocal, that minus 1 exponent, reciprocal of x. And this is going to be 8 times negative 2. So not just the reciprocal, but a squaring there as well. And now after that, a little bit of legwork, we're able to just go ahead and differentiate all 3 pieces using that sum and difference property, sidestep those coefficients. using that constant multiple property, and of course most importantly utilize our power rule there, because now we have a constant function and two power functions. So let's go ahead and differentiate this. So now our derivative, and again I'm going to put in all these differential operators and do this in a lot of detail, since this is our first video utilizing all these basic derivative chops. So take the derivative of 1 and then move on from that and deal with the next piece after the subtraction, which is taking the derivative of 6 times x to the power of -1. And then we'll move past the addition and take the derivative of 8x to the power of -2. So there's the sum and difference property. And then what can we do in the next step? Well, we'll bypass those coefficients, which is that constant multiple of a function property. And I'll rewrite this one. It's just going to be derivative of 1, which we'll deal with in the next step. And then we're going to bypass that 6 and go right to a fairly plain power function. As plain, I guess, as we can make it in this situation. So just a basic reciprocal function, x to the power of -1. And then we'll bypass this coefficient 8, and then we'll take the derivative of as plain of a power function as we can deal with here, x to the power of -2. If I can put that in white, I guess, to be consistent here. So again, if you're thinking of these two steps instead of writing them, it's probably far more efficient, but in the interest of, I guess, understanding here and following me, I think I'll just add those two steps to this video. So now let's finally go through and differentiate our terms. So the derivative of a constant, remember, is 0, because that is a constant y equals 1. It's a horizontal line with a slope of 0 everywhere. And then, I guess after the 6, we can put the derivative of x to the power of -1, which is going to be -1 in front of our x, and then subtract 1 from our power. And then we're on to the last one. After our 8, we'll take the derivative of x to the power of -2, which -2 comes down in front, and then your power decreases by 1. And there's our derivative. Now we do have to actually evaluate this derivative, so we better clean this up some and maybe get away from the negative powers there and write them as fractions as well. So now, at least in one color, which won't slow me down as much, there's no sense writing 0. We're going to have -6 times x to the power of -2, so that's +6, x to the -2, plus, I guess I better not say plus, because there's a negative there. 8 times -2, so that's going to be negative, or subtract 16 times x to the power of -3. And now we can write our derivative. Maybe we'll look at all of that. We'll write our derivative one more step. Maybe not one more step. Let's see what we can do. This will be 6 over x squared. Going back to our fractions, subtract 16 over x cubed. Getting a little tongue-tied here with my pen. There we go, over x cubed. Now if you want to write that all as a single fraction, go for it, but I think we'll actually leave it there. That's good enough, and we can evaluate this function. I should say this derivative now, and I think it was x equals 3. Yeah, x equals 3. We'll see what's happening with our slope of our curve at x equals 3, so I guess we'll go all the way up to here. So evaluate our derivative at 3. Find the slope of the curve at 3. And then with whatever work we have to do with fractions, we can do it when we have numbers. It's probably easier. So we have 3 squared on the bottom, which is 9. And then we're going to have subtract 16 all over 3 cubed, which is 27. So we can of course reduce that first fraction, but looking at the second, we can't reduce that. So let's get a common denominator here, and we'll multiply the bottom and the top of that function by 3, and then we'll get 18 all over 27, writing this as an exact slope, which I guess is maybe not required, but it's good to have your fraction chops, I guess, up to speed. So this looks like it's going to be 18 minus 16, which is 2 over 27, and this is our derivative evaluated at 3. And of course, remember, that's the slope of our curve. Okay, so in those two examples, we can see that we can definitely use our power rule in situations that, as I said, at first glance, looks like the power rule is not an option, but with a little bit of work up front, you can manipulate your function into a sum or difference of power functions. And then, of course, your power rule is very much in play, and it's a most efficient way of differentiating these functions. And just to make sure we're clear on that last slope, I'm going to, as we wind out this video, I'll show you how to find your tangent slope of this last function we did here on your TI Inspire.